Gradient descent is the algorithm we use to minimize the loss and improve the model's performance over time. In the previous video, we introduced the loss function, a way to measure how wrong a model's predictions are. Now that we know how to qualify the error, the next step is figuring out how to reduce it. Gradient descent does exactly that. It systematically updates the model's parameters to drive the loss down step by step. To understand how it works, we need to look at gradients. To figure out which way to move in, we compute the gradient of the loss function for each parameter, both the weight and the bias. Since we are dealing with two parameters, the gradient is best understood in 3 dimensions. One axis for the weight, one for the bias, and the third for the loss value. This way we can visualize the entire loss surface and how the parameter is affected. These are called partial derivatives, and they point in a direction where the loss increases the fastest. So to reduce the loss, we move in the opposite direction of the gradient. Here is the update rule we apply. This formula tells us, take the current values of weight and bias and subtract the fraction of the gradient. The fraction is controlled by alpha, the learning rate, a small constant that determines the size of each step. If alpha is too small, learning is slow. Like very slow. If it's too big, we might overshoot or diverge completely. Each update moves us closer to the bottom. At first, the steps are large, but as we get closer to the minimum, the gradient becomes smaller and the steps become more precise. But it's not always that straightforward. Sometimes we face more complex surfaces with multiple local minima, and our goal is to reach the global minimum without getting trapped in one of the local minima. We'll explore those kind of examples in future videos. There are 3 common ways to run gradient descent. Batch gradient descent computes the gradient using the entire dataset. It's accurate, but slow and memory intensive. Stochastic gradient descent uses one training example at a time. It's faster, but more noisy. Mini batch gradient descent computes the gradients using small batches. It combines the benefits of both and is used in most practical models. Now let's talk about the term optimizer. An optimizer is the component that updates the model's parameters based on the computed gradients. Gradient descent itself is a basic optimizer, but in practice, we often use advanced optimizers. They are algorithms that improve on gradient descent by making the updates more efficient, adaptive, and stable. These optimizers help models train faster, converge better, and escape tricky situations like saddle points or local minima, as I mentioned before. Let's look at some examples of popular optimizers. Momentum remembers the previous update direction and builds speed. RMSprop adjusts learning rates for each parameter based on recent gradient magnitudes. Adagrad adapts learning rate based on past squared gradients. Adam combines momentum and adaptive learning rates. These optimizers are especially useful in deep learning, where the loss surface is complex and high-dimensional. Gradient descent is a core learning algorithm behind most models, and optimizers are the tools that make that process more efficient and effective.